So let's take a look at another one. Let's look at matched problem 1. We have the function x minus 3 over x squared minus 4x plus 3. They're asking us to describe the behavior of f at each 0 of the denominator. So if we were to set that denominator equal to 0, we're going to get x minus 3 times x minus 1. So x is going to be equal to 3 and 1. So let's start by finding the limit as x approaches 3 for this function. So if you notice here, if we were to plug the 3 in, we're going to get 0 over 0. So that's that indeterminate form that we talked about in the last section. And what that means is we need to try to factor and reduce. So if we look at this, we do see that something's going to factor and reduce. The x minus 3's are going to reduce. And that's going to leave us with the function 1 over x minus 1. So if we were to evaluate that again, using that reduced function, we're going to get 1 over 2. So what this is saying is as x gets close to 3, those y values are getting very close to the value of 1/2. But if we were to look at what's happening at 1, we're going to see something a little bit different. So notice in this case, we're going to be dividing by 0. So that's a key to let you know there's something a little bit more interesting going on with the graph at this particular x value of 1. So let's look at left-hand and right-hand limits. So if I take the limit as x approaches 1 from the left, and it doesn't matter if I use the original function or the reduced, I'm going to get the same answer. And I'm going to look at the limit as x approaches 1 from the right. So let's think about that number line. Here's the value of 1. As I get close to 1 from the left-hand side, I'm looking at values like 0, 1/2. And if I get closer, I could talk about like 0.9, 0.99, 0.999, and so on. So going back to my calculator, I've got my function typed in here. There's my graph of the function, and we can already see what's happening from the graph. This is going to go down to negative infinity on the left-hand side, but let's use our table. So I'm going to delete these numbers. I'm coming in close to 1 from the left, so 0.5. I really could start at 0.9 if I wanted to, and then 0.99. The idea is to get really close to 1 on that left-hand side. And you can see what's happening. As I get close to 1 from the left, all those y values are getting smaller and smaller and smaller and smaller. So we are definitely heading towards negative infinity, which is what was indicated on the graph. Now, if I want to get close to 1 from the right-hand side, I'm looking at that right-hand side, getting close with numbers like 1.1, 1.01, 1.001, and so on. So if I go back up, 1.1, 1.01. You can see how these numbers are getting much, much bigger the closer I get to 1. And that's not quite at 1, but the closer I get to 1, the bigger those y values are getting. So this side is heading towards positive infinity. So I see that unbounded behavior as we approach 1 from the left and from the right, which means we've got to have a vertical asymptote at that value of 1. That's what's going on there. So look at what's going on. Let's kind of analyze what's this a little bit more, and let's look at a theorem. Theorem 1 is talking about locating vertical asymptotes of rational functions. If f of x has a numerator and a denominator, so that it's a rational function, and the denominator is 0, but the numerator is not 0, then it turns out there's a vertical asymptote there. So it really depends on what's going on in the numerator and the denominator. So first notice, this is not the factored form that's been reduced. This is the original function that they're talking about here. What they're saying is you could kind of use this shortcut. If the top is equal to some number that's not 0 and the bottom 0, then you're going to have a vertical asymptote at that value. And we can see that when we looked at this limit as x approaches 1. When we plugged in that value of 1, we got -2 on the top but 0 on the bottom. And that let us know that we are going to have a vertical asymptote here. And we showed that unbounded behavior by looking at the limits as we approach 1 from the left and from the right. Now, when we substituted in that 3, we ended up with a 0 in the top and a 0 in the bottom. When that happens, you'll actually have a hole. And that happens at the point, the x value, which in this case was 3, and that y value is really that limit, which was 1/2. So this is where that rule from 171 really comes from. An equivalent way of saying this theorem. Let me see if I can find a place to write. And this is what we told you back in 171, is that you could factor, and then you could reduce, and that gets rid of anything that would give you a 0 in the top and a 0 in the bottom, which is where your holes are. And then you could set the denominator equal to 0, and that's going to always be your vertical asymptotes. So that's an equivalent statement to what we just talked about in Theorem 1. So let's look at another one. Match problem 2, we want to know behavior at the zeros in the denominator. So again, if we were to set that denominator equal to 0, we're going to get -3. So we're really asking, what's the limit as x approaches -3 from the left and from the right for the function? So I'm going to go back to my calculator. I could just look at the graph. As we approach -3, you can see unbounded behavior on the left. This is going to -infinity, and on the right. But if we wanted to prove it, we could always go to the table, and we could fill in the table. So if I'm approaching -3 from the left, let's go back to our number line idea. So here's -3. If I'm coming in from this left-hand side, I'm getting close by looking at -3.5, maybe -3.1, -3.01, and so on. So here's -3.5, -3.1 is even closer, -3.01. And you can see that as I get closer to -3 from the left, I'm heading to -infinity. And we would say the same thing from the right-hand side. If I'm coming in from the right, here's negative 2. So I'm like negative 2.5, negative 2.9, negative 2.99, and so on. So you can see how we're really heading towards negative infinity from the right-hand side as well. So this is showing unbounded behavior, negative infinity. And since we have unbounded behavior, then that means we have to have a vertical asymptote at x equals negative 3. That is our conclusion.